This is the next protocol under serial communication, which is quite popular, which is the serial peripheral interface protocol. Okay. See here, this is popularized by Motorola. Okay, and obviously this is synchronous. So in addition to the data line, definitely there will be. And the important aspect of this is there is a separate transmit and separate receive wire. So that is a full duplex communication. Okay, so this SPI is a full duplex communication. And essentially, if you count the number of wires, one for clock, one for transmit, one for receive, there is one more wire to select the the receiver. So there are 4 wires involved. And as we said at some point of time in communication, there is this concept of transmitter being considered as master and the receivers being considered as slaves. So in this case, multiple slaves are possible, but typically a single master for the case of SPI. And 4 wires, so we will discuss on those 4 wires in detail in the next aspect. So the general description is something like this. So this is the master, for example. So we set it as slave also, so it is completely configurable. The moment we set it as master, it will always behave as master. So one master here and multiple slaves here. So I've given 3 slave options here. This is illustrative example. So the 4 wires, so one is clock, the other one is master output, slave input. So this is output from master and input to the slave. Okay, so MOSI. And then master input, slave output. That means it is input to the master and output from the slave. So these 3 are the typical wires, and then 1 wire for selecting the slave. So we call it as 4-wire communication, but if you have more number of slaves, the number of slaves select will increase. So basically, typically, in the case of this sort of configuration, one of these slave select will be going low. So that slave will be, and remember this is negative logic. So if it is going SS1 going low, means this slave is connected. These 2 are disconnected. So typically one of the slaves will be connected, but there is a possibility that you want to send the same data to 2 slaves. Then of course you can enable both the slaves together. And then the data transmission happens based on the clock, and the output data will be given to this terminal and input data will be taken from this terminal. So that is the concept. So this is the typical configuration, but there is daisy chaining also possible, which is something like this, where one slave will be connected to the other slave. That's something like this. So again, the slave select pin is controlled by the master. The clock is also given individually to the slaves. But here, this MOSI pin is connected to the MISO in the other case. And then here, the data out, or in case I think typically it is the MISO pin will be. So if you want to give some data to this from the master, you cannot directly give. You have to give that data first to slave 1, again further circulate it to slave 2, then further circulate it to the desired slave. So it is something like daisy chaining, which you learned in digital systems. Okay, so 2 configurations are possible. But again, just to highlight it, it is a 4-wire communication. 1 for data transmission, 1 for data reception, 1 for clock, and 1 for slave selection. Okay. Moving forward in slightly more detail, this is what I was talking about. So the naming convention is something like master output, slave input, MOSI. This carries out the data from the master to the slave. Master input, slave output is MISO, which carries out the in data from the slave. So for MOSI, the data transmission is from master to the slave. For MISO, it is from slave to the master. So this is a full duplex. Remember that. Okay, full duplex communication. Dedicated wire is for transmission as well as reception. Okay, and interesting fact is that you can make it happen simultaneously. So you can have a transmission from master to slave as well as slave to master simultaneously. It is possible. Okay, and then of course slave select. This is negative logic, so that's why slave select bar, and this is the unique line to select the slave. It's very important. Okay. And there is a clock, okay, to synchronize the transmission. Okay, so this is how it looks like internally. If you go a slightly more in-depth picture, we have a very detailed description for freedom board, but it's so complicated, right? So this is the entire concept. So what happens is from the memory, you load the data to your register, data register in the SPI. That will get transmitted to the data register in the slave with clock. So each clock cycle, you get 1 bit of data transmitted. And at the same time, it is possible to transmit the data from the slave to the master. Okay, so that is possible. So everything goes by clock. It's not like the UART where actually you have a start and stop bit to synchronize the transmission. But here there is a clock. There is no need of a start or stop bit in that case. Okay, and the important aspect is that only a master can start the data transfer. That means you cannot push the data from slave to master. If you want to transmit data from slave to master, you have to issue a read command. That means you have to read from the slave, then only the data transfer happens. Okay, so master is the key, and the name suggests that, right? It is the controller. So it issues write or read operation. Based on that, data get transmitted. Okay, so that is the concept. So this is how it happens. Each clock cycle, 1 bit transmission will go. And before that, you have to ensure that your slave select signal is enabled. Otherwise, it doesn't know where to transmit the data, right? So you have to enable the slave. So you select the slave, then you issue write or read command. Okay, so this is basically the write command, and this is the read command. Okay, so that's the concept. So it is interesting to see here. So the most you can actually control it. So even though I shown that the first bit to be transmitted is the most significant bit, but that's not the case. There is a provision for you to control whether to transmit the lowest significant bit or the most significant bit. But you fix it, that will be continued throughout a certain transmission. Okay? You cannot change in between. Okay? You decide, typically most significant bit is transmitted first, but that's not all the time. It is configurable. Okay, so you can see this is interesting. So 7-bit, let's say it is simultaneously happening. So 7-bit gets transmitted at the same time, the 7-bit gets transmitted from here, and everything gets shifted by 1 bit, so that this guy, or I would say this guy will come and sit in 0. By that time, everything gets shifted by 1, so that the 6th guy is at 7 and 0th guy is at 1. So you're not losing the data. Okay, and here also 7 is transmitted, you're pushing it, so 0 will come to this 1 place, and this bit is ready to take the new bit from 7. So there is no problem of data missing or data clashing. This is an example where I'm sending 2 characters S and F, and this is S is transmitted from master to slave, and F is transmitted from slave to master. So let's see how it happens. So S is equivalent ASCII value is 53. 53 corresponds to, this is from most significant to the least significant. 5 is 0, 1, 0, 1, it is here, and 3 is 0, 0, 1, 1. So it will be getting transmitted. Similarly here, F, which is 46. So 0, 1, 0, 0 is 4, and 0, 1, 1, 0 is 6. So that's the key part. And the important part is there is an ideal state I would say, where there is no clock. Okay, so clock is disabled during the ideal state. The moment clock starts, data transmission happens. Okay. So you can decide the order of this transmission also. That is possible. And you can see also the slave is only selected during the duration of data transfer. So it's interesting, I would say, that you go now with the C code, it's very easy for you to program, and if you Google search, you will find a lot of codes to start with, but don't use it blindly. You understand this concept, experiment yourself, everything thoroughly, okay? And then you will understand the concepts very clearly. So we will not be having any lab session dedicated to SPI, but after this, I will just quickly show you how SPI is enabled so that it becomes very clear to you. Okay, so let's move on. And this is what is inside a freedom board. It looks very complicated, but it's very, very simple, because you really don't have to worry about how this is arranged. All you have to worry about is to understand how to configure these registers which are associated with SPI. Similar to how we did for interrupts, similar to how we did for timers, similar to how we did for UART. Here also everything remains same. Okay. So just to give a brief idea of what is this looking like. So the pins are here. You have MOSI, MISO, clock, and slave select here. And this is your data buffer. So your CPU will write to the transmit buffer using a store command. So you store that data here, and then issue the respective command. The shift register will take one at a time, and it gets shifted to the MOSI and it goes to the slave, right? And if some reception happened, so the MISO will take the data, it will get into the shift register, it will get stored in the read buffer, and you issue a load command in the CPU to load from this register, you will get the data. So that is how the concept happens. This is to enable the SPI. Please go ahead and do that. All these commands are there inside these registers. All these values we can set using these registers. And if you see here, the clock control is here. So there is a baud rate control as well. You can control similar to that in UART. So this is a clock rate. The rate at which you want to enable the transmission is configurable, and it's in full control for you. You can do it using software. You don't have to change anything. And this part, the bottom part, is to enable the interrupt and also to enable direct memory access transfer. So we'll have a small discussion on DMA. It is an advanced concept. So DMA is something like conventionally, how does the transmission or the communication happens? The slave will take or some sensor will put the data into your register, for example, in this RX buffer, and then you use the load command to read from this register. So everything is going through the CPU, right? So you load from the sensor to the memory, and then from memory you do something. So you want to avoid that. You want actually the peripherals to have some access to the memory, not necessary through the CPU. So there is a possibility, and that is known as direct memory access. So peripheral to peripheral communication through memory without the help of a CPU. So we will discuss on that, okay? But very brief, we don't go into details of that, but somebody is interested, again, it's very easy nowadays because you will get a lot of simple hands-on code where you can experiment with it. But the concept, you have to be very clear. Okay, so now let's briefly, I just want to briefly go through this manual. Okay, so you see here, so I'll just click on again, the Freedom Board manual. You click on chapter 37, which is on serial interface. If you go through, okay, so this is how it happens on the master slave side, 4-wire communication, everything it is. This is the details of the Freedom Board layout we just now discussed. And this is the register. So it is important that you go and understand each of these registers. I have a sample code here, so we'll go through this to basically make sure we understand some of these concepts. Okay, so this is how easy it is. I'm not using assembly. If somebody is very keen, you can do it in assembly as well. It's slightly more tedious, but that will be a huge learning experience for you. But here it's a simple C code for you. So these are, again, I can put it into something like SPI .h. If you want to do that, you can do that. But otherwise, just make sure that these functions are visible to the main function. That's key. Okay, so in the main function, I'm initializing the SPI, and then I'm writing something to the SPI. Okay, and the data is these two. Okay, so this is the data I want to transmit, and then this is the address of SPI, which is something like we enable the SPI S bar pin or something like that. Okay, so two data, the size of data is 2, so I have 2 data to transmit. Okay, I would say 2 bytes of data, right, to transmit. And this is the SPI initialization, this part. Okay, and in this I'm actually doing much more than that. So here, if you see SIM SCG5, this is nothing but I would say the port D. So I'm enabling the clock to port D. So this why this happens is because port D's pin is used for, or is configured as what? Okay, maybe I'll run it so that it's become very clear. No need to actually go to the manual because everything is here, so no error, fortunately. So let me. Okay, so I'm just going to run in the debug mode so that it's very easy for you. Okay, so we are here at the start. Okay, so let's do what it is happening. So SDG5, it's pretty known to you what is it. So I'm just going to enable the clock of, because that is the pin that is used as a serial interface. Okay, because the pin, this SPI is mapped to a certain pin in the freedom board, right? So that pin forms part of the port D. Okay, so I'm going to enable that. Okay, so this is clock is enabled. Let's see what is SCG C4. Okay, so SIM SCG C4. This is SPI 0. So I'm enabling SPI 0's clock. So that's also important. Now these are the pins basically, which is actually configured as SPI or mapped to SPI port D's pin basically. So port D's 0, 1, 2, 3. Okay, so these 4 pins are actually, uh, if you see here, so one is GPIO, I think 2 probably will be your pin for SPIO. Okay, so this is basically enabling that. Okay, let me just quickly go to let me just quickly go to the. So this is the freedom. This is the best place to go because it's easy to do that. So I just wanted to show you here. So what we are actually configuring is port D's PCR 0, 1, 2, 3, right? So where is the serial protocol? So port D's 0, 1, 2, 3. So port D's let's say port D1 is clock. Okay, so port D is 1 is clock. This is MOSI. Port D is 2, pin number 2. Is that correct? Let's see that. Yes, and port D3 is MISO. And port D0, I am using it for slave select. Okay, so that's the thing. And then I'm going to configure these registers in SPIO for certain things. So these registers are mentioned here. So here, for example, SPIE is to enable the interrupt, which we are not going to use at this point. SPE is to enable the SPI, so that definitely we need to put 1 here. SPTI, transmit interrupt, I'm not going to enable, so this is also 0. And then master slave, so I'm going to use this as master, so it has to be 1. So this will be 0, 1, 0, 1. So basically 4 plus 1, 5. So this has to be 5. And this one, let's see what will go about. So CPOI, clock or polarity, I'm not worried. Clock phase, I'm not worried. Slave select, output enable. So if it is 0, in master mode, slave select is general input output, not SPI. But this is more important. In master mode is input for mode fault. Okay, so slave select input. So it will act as slave select input for 0, but we are actually in master mode. This will be automatic slave select output. Okay, so this is what I want. So, and then LSFP, I'm just going to this, I'm not interested. This is where I was telling you that you can shift the direction of a bit from more significant bit to less significant if you want to do that. But I will go with the more significant bit, so I don't want to touch it. So basically this will be 0, 1, 0, 1. So this will be 5 and this will be 0, 0, 1, 0. This will be 1, sorry 2, right? So it will be 5, 2. So that's what I'm doing here. So 0x5. And similarly C2, I'm not interested in changing anything, but have a quick look at what is C2. So many options are there. I'm not going to change anything. But if you are interested, please go through this and then you can set the baud rate. Okay, so I'm going to select this for the moment. Okay, so V2 is 0. So this will be 0. And here I'm actually putting 1 somewhere. So let's quickly see that what it is. So 0, 0, 1, 0. Okay? Sorry, 0, 0, 0, 1. So mode fen I'm setting it. So I'm putting as 1. So mode fault enable master acts as the mode fault input or save select output. So that's what you want, right? So that's the thing. So you configured all these 3. And basically what you did is you you enable the SPI, then you decided on the whether you want to enable it as interrupt or not, which I did not. Then you enable the slave select, and then in this case you have to enable the slave select again, and then you set the baud rate here and you're set. you're done, right? And then you just scroll down here. You have status register, which you can use it to see whether your transmission is done or reception is done. And then there is a data register where you will have the data to be transmitted. Okay, so that's the thing, or received. So the same data register will be used for transmit as well as receive. So that's the thing. And then you have the write operation here. So what you do actually is the size you already mentioned. So I'm giving, for example, here data with the size and then some address. Okay, so this is the configuration that you have. So this is a pointer to that data with the size this. So basically you assign that data to the register, and then you enable the clock already. So as long as that register is full, that means data transmission has not happened, you will not assign new data to that. That's what the meaning of this. Similarly, there is for the reading operation. Okay, so you can do all these and a lot more actually. So this is a very simple case here, and that is a demo for that. I think we will stop here before we go to the I2C. I just wanted to make sure that we'll go slowly on these three aspects. I2C will be a smaller lecture because I really don't want to go in details of any demo there. And we'll stop here. So this is the lecture on SPI, dedicated to SPI. And if you have any questions, feel free to raise them in the discussion forum. So yeah, so please go ahead, and I would suggest that you experiment with this. And later on, at some point of time, I will introduce you to a simulator in the embed system, embed cloud, which is actually sort of generic. It's not restricted to KL25Z, but it will be useful for you. Okay. So I would highly encourage you to try it out either in embed, which is much simpler. But my suggestion is to try out in Keel, which is slightly complicated, so that you understand the protocol. Okay. So that's the thing. So we'll stop now, and looking forward to seeing you in the next lecture. Thank you.